what you will learn from this talk. So I'm going to cover the overall concurrency landscape briefly, so that you understand it. You'll see a view that you probably haven't seen before, but it's the right view, and I'll explain how everything hangs together. And I work for Hotels.com, which is part of Expedia, which is the largest travel agency in the world. So one of the things I'll show you some great places to go on holiday as part of this talk. So this is the agenda, and I'm going to look at the levels of concurrency. So you understand, you've probably seen like these low-level things and these concurrency models and patterns, and I'll explain all of that. And then I'll go into explaining what the problem is that you're solving, what the problem is that you need to solve, and then the various patterns that I'm going to talk about, the 4 patterns, and then I'll put it all together for you so you've got a step-by-step guide of what to do and how to deal with it. So this is the first section. And before I go on, we have at Hotels.com, we have a competition. People can send in their photos of their holiday, and the best one every month gets to be a winner, and there's a prize involved. I can't remember what. So this is one. All the pictures you'll see are winners, and this is the Bellagio from a guy who's traveling in Italy. If you get the slides, if you look at the bottom of the slide there, I'm not sure if you can see it, there's a link which will allow you to download the slides, and you can get all the slides, you can get all the pictures with all the links that'll tell you exactly where these are. So I'm going to start with concurrency patterns, models, frameworks, techniques. You keep hearing these. Actually, they each have a different meaning. So there are 3 levels of concurrency. There are the models, which, if you went to Russell's talk earlier, the last talk in the morning on concurrency, that's what he was focusing on, the different models, the concurrency models, and I'll list them all in a little while. Just a single slide. I'm not going into any detail on those. And those models are implemented with frameworks. So that's the model and the frameworks. Then at the medium level, and that's where I'm going to go into some detail, are the patterns which you use within those models, and at the bottom level are the techniques where you actually build everything if you're going to do it all yourself rather than use a model. So just starting at the lowest level, there's a lot of techniques, right? And if you're, not if you are Java programmers. So when you started learning Java, the first thing you learned as far as these concurrency techniques was concerned, it taught you about runnable, and then starting a thread with a runnable, and maybe they taught you thread group, and then they went into synchronized, and you learned about object wait and notify. So I've done all that sequence there. It gets more and more sophisticated as you go along. And then if any of you, hands up who's heard of @contended, which is a fairly sophisticated thing. It's the end of that first line. So that's really sophisticated. That is talking about cache level concurrency at the CPU. So if you know about @contended, you probably don't need to come here. You already know maybe more than me. It's fine. But these are the kinds of things that you learn as you get more and more sophisticated at the low level building blocks. And then there's a whole bunch of different collections, and you can go through all these, and each of these collections provide different types of concurrency capabilities, and they're all useful. It's quite interesting if you want to find something that works for you. Look through all the various collections that I list here, and then you'll probably find something that already solves your problem. But it's useful understanding that there's this lower level. The medium level here is the one that I'm going to go into some detail. There's the 4 concurrency data control patterns. I don't need to list them. And these are built from those low-level blocks we just saw. And it's worth noting they're not mutually exclusive. You can use these in combination with each other, and I'll show you that at the end. So there's no more on this slide because that's what the talk's about. And then the high-level concurrency models. Now this is quite interesting. There's a book a couple of years old now called 7 Concurrency Models in 7 Weeks, which was quite influential in making people understand that there are different concurrency models. But in fact, when I went through that and I realized there's another 3 that are, so these are common. There are loads more, but these are the common concurrency models. This is what Russell was focusing on this morning, if you went to his talk. And I'll just list these in a little bit more detail. And what I've done is I've changed so that book doesn't look exclusively on Java. I think only 1 or 2 of them are in Java. I've given you the Java version for everything here. So the first one there is do it yourself. Do your own threads, do your own locks, do your own synchronize. That's the standard thing you're taught. And that's a concurrency model, which is basically you have to build everything. And that's hard work. Then the next one, I'm just going in the order of the book. So the next one was functional programming. That's the stuff that was released in Java 8, streams, Lambda expressions, and also RxJava. If you use that, it's the same. It's just an additional options for external ones. So I don't need to go into detail there. You've probably been to half a dozen talks on using streams. The third one listed there, atomic and thread local. It's also kind of still at the building block level, because we're talking about atomic classes and thread local classes, and these are still you're building yourself, but it's a little bit more sophisticated than the threads and locks, and it's trying to avoid locks within your concurrency mechanisms. So this is called lock-free programming, and we'll touch one of the patterns I look at will explain some of that. The next one is actors who use akka. That's the most common one. There are a lot of other actors too, but akka is the most common one for Java. All of these have different advantages and disadvantages. Actors' problem is that we're not really well formed for handling event-driven stuff. So if you build a lot of actors, it gets really complex and you start to not understand it. And then communicating sequential processes, that's the thing that was popularized by Go. But in fact, there's the Quasar framework that's been around in Java for quite a while, and that is now being put into Java. So if you were at Russell's talk, he mentioned Quasar, and he was asking, is Java going to catch up? The answer is yes. It's called Project Loom. It's basically plugging Quasar into Java so that we will have communicating sequential processes. There are lightweight threads, and is a different way of thinking about it. And that's kind of working now. They haven't done 3 or 4 of the things that they need to do, but that's already working. So there's like an initial version that's available for Java 12, but it's probably not going to be ready till Java 13, maybe Java 14. So we're talking about a year and a half down the line, I would say. But it's based on the Quasar stuff, although they're doing it from scratch, but it all works nicely, and I expect that to be pretty useful. Then data parallelism, that's kind of using GPUs, just slam your arrays of data, execute everything the same way on all the data to the next stage of the data pipelines. That's the 1, 2, 3, 4, 5, 6th, and the 7th from the book is MapReduce, which I'm sure you've all heard about. And there's 3 more there that weren't listed in the book, but they're also very common, especially in Java, which is 2 event-driven models. There's the single-threaded one, which is most popular outside of Java as Node.js. And in Java, there's the Vertex framework. And then the multi-threaded one is the Kafka version. Kafka is the equivalent for the multi-threaded. And then finally, there's a grid computing concurrency model. So those are the high-level concurrency models. It's interesting to see them all, but I'm going to focus on the mid-level one. So before I go into those patterns, there's a nice bridge in Bosnia-Herzegovina. I think it's got a story behind it, but I can't remember what it is. I'm going to talk about shared mutable state, which is 3 different words. And you think to yourself, okay, it's buzzwords. What does it mean? It's important. Every single word there is important. So clearly, state is data out of some storage, some value of data in storage some value in storage. Okay, mutable just means that it is being changed. It's not something that's you write once and you never touch it again. It is being changed. That's what mutable means. And shared means, in this context, more than one thread will access that storage location. So each word matters here, because if you can get rid of any one word, then you've got rid of the difficult bits of concurrency. So that's why, keep in mind, shared mutable state, you want to get rid of one word. It makes it much, much more easy. Sorry, not. So example is shared mutable. I'll start with state. Obviously, if you get rid of state, you've got no concurrency problem. You might need to synchronize across threads, but it's not a problem. It's quite straightforward and easy. So that's really the jackpot. That's why stateless servers, stateless everything is the target. And it's spectacularly difficult because not very many applications have no state. Most of them have state. But there are a couple of things that do apply to a lot of applications. And one is that you can separate out the stateful parts of your application and the stateless parts. And that means that the stateless parts are really easy to scale. And the stateful parts are where you can concentrate on the concurrency. The other is that you can all push the state to a data store. And there's like a zillion different data stores. And this is the reason, because each type of data store does a different thing for you. So it makes it easier. And those are kind of different concurrency models, but they're not really. They're sort of variations on that first locking concurrency model, if you do that. So the second word there, mutable, if we can get rid of mutable, then again, you've got no concurrency problem. So that's immutable objects, immutable things. It's difficult, but it's not impossible to make your application use a lot of immutable objects. And there's also, bear in mind that you can make things effectively immutable, because certainly stuff that you initialize you're mutating it for a while, but eventually it settles down and then you no longer need to change it. That's effectively immutable. You can actually make it explicitly immutable by copying it the whole structure into something new that is immutable, or even if not, the JVM actually begins to get quite efficient on things that you aren't changing at all. So it's worth thinking about whether there's some parts of your application that are effectively immutable, and really just push that off so that you guard it so that it doesn't get any changes to it. If you want to do immutable objects, just look it up, because it's a little bit fiddly. You need to do final, private. And the more difficult thing is that any field you have in your immutable object referencing another object has to reference an immutable object. Otherwise, it's not immutable. So if you're referencing an array and you change an element in that array, then your object is it's not immutable. It's just something that is pointing to other stuff that can be changed. There is an inefficiency from immutability because you have to tend to copy objects. That's how most immutable applications run. They make copies of objects, so they don't change the objects. And that means that there's a lot of pressure on the GC from all the extra objects. But typically that's much more efficient in a highly concurrent situation than trying to work through all the bugs that you otherwise get. And then the first word there, shared. Again, if you're not sharing it, there's no concurrency problem. So that's nice. But you can do things like thread local state. So thread local, one of the things you learn about early on. If you can put everything in thread locals, you might get a memory leak, but at least it won't be a concurrent problem. Now, going back to those models, those 10 concurrency models. The reason that they are very popular is that a lot of them try and avoid one of those words. So if the ones that are trying to avoid mutability, that's the functional programming, streams and lambda, it does a lot of copying of objects. MapReduce tries to avoid changing objects. And in fact, the concurrent sequential processes also do but I don't really have enough patterns within Java yet, so I haven't included in there. And then the other ones like actors, single-threaded, event-driven, they try to avoid sharing. So clearly, if single-threaded means there's no sharing, it's all in one thread. The actors put all the changing, the actor does all its changing on one thread. So again, you're there, data parallelism, map reduce. That's why these concurrency models are useful, because they get rid of one of those words, and it means that you have made your concurrency problems much, much easier. Okay, so now I'm going to go into the concurrency control patterns. Did I skip a picture? Oh, you can get the slides. This one is Baraza in Zanzibar, which is fabulous. Isn't that like picture? Anyone going to Zanzibar? I'll join you. Okay, so I'm going to use an example which is simple and real world. It's very unusual to get that. I'm going to use a business process object, and it's going to have an identity and some state, some internal state, and processing. So its objects will be accessed by identity, and the new information can be anything. So it's quite a generic thing. So I'm going to flip over to the code so you can see what I'm talking about, because some people prefer the description, some people prefer the code. So here is, I'm going to hold the state in a data variable in a single-threaded version. As you can see, if you store the business object, you just get its identity, use that as the key into the map, and then put the objects as the value. And then when you process an update, you take the identity, you get the update, whatever it is. Here I'm using a double, but it can be anything. And then I go into the hash map, I access the object using the identity, and then I process the update. Okay, so I'll flip back to, let me explain again. So it's a business process object. And it's very generic. Probably half applications have exactly this kind of thing in there somewhere. Okay, so it's quite straightforward and quite simple, and actually quite real world. So this is Antelope Canyon in Arizona. It's a nice little place. So I'm going to go into the first of the patterns, which is pessimistic locking. This is still my single-threaded implementation I showed you just a second ago. And I'm going to flip over to the DIY pessimistic locking version. There. Okay, wait. What changed? I don't know. So let's flip back and forth. I'm just going to flip back and forth. If you look at the first line, the data line is exactly the same. If you look at the code within the methods, they don't change either. They're exactly the same. So if you look at the method declaration, I've added the word synchronize to the method declaration. Okay? That's all there is. So there's no change to the code, just we've specified synchronize. And there's a very good reason why it's like that. It's because what synchronize does is it makes that set of that code into a serial as in executing one thread at a time. That's exactly why the code doesn't need to change, because all I've done is I've said, it doesn't matter how many threads you're going to have, only one thread at a time is going to go through this code. That's what synchronize does for you. So that's why the code doesn't change. Only the entry points and the exit points needs to change. It's nice and simple, very easy. It's got some benefits there. It's very easy to understand and very easy to think about. And the JVM really understands locks and monitors really well. And there's a reason why the JVM understands. It's not because it's natural or anything. It's because if the Java community uses something a lot, then the JVM compiler guys actually go and try and optimize those things. So over the decades, we've used monitors and locks a lot. So there's been a lot of effort in optimizing that. And now it's very good. You can get some excellent performance on the JVM monitors. Of course, there are disadvantages. Primarily, you have made this into a single-threaded section of your code, which means that you're not getting any parallelism. It's not happening in parallel. Everything is going to go through that one at a time. And although it seems to be quite easy to implement and avoid a bug, In fact, if you start letting data structures escape the class, if I go back to that one, if I have a method somewhere that returns that data element, the hash map, then something else can access that and start screwing around with it. And that wouldn't be thread safe. So it's quite easy to introduce bugs as you go. We're talking about tiny little application here. Of course, it doesn't matter, but in a larger application, you might forget, oh, I need to access that data structure. You just make it available, and then immediately somewhere down the line, it's a maintenance problem, and there's bugs. So it's kind of easy to introduce bugs. And it's very difficult to minimize that lock time. So remember, we've made it serialized. We've made it execute on a single thread through this code. So you want to minimize that code. You want to minimize the time it's spent in there so that all the rest of the code can run in parallel. But it's quite difficult to minimize that. And this is Quahog in Krabi, Thailand. I bet you have. Hands up if you've been to Thailand. Yeah, that's good lads and ladies. Pardon me. Okay, so we're going to go into the second of the patterns. And again, this is the single-threaded implementation. You should be used to. That's our business object. And I'm going to flip over to an optimistic transaction version. So again, you want to see the differences. I'm going to flip back and forth between them. That first line, the hash map, has changed to a concurrent hash map. Okay, that's kind of what you'd expect, really, because we're talking about optimistic, so it's going to try something and do it. And concurrent hash maps works beautifully for that. And the second line, actually the same. The third, in fact, everything else stays exactly the same. That's the only thing we changed. Now, that seems to work, except there's a subtle bug if you just do that. So when you get down to processing the update and you do the bids process value in place, if you have two threads executing that at the same time, each of those threads will process that update on the same business object, and only one of them are likely to win. I mean, they might both win, but it's quite often that one of them will win. So you'll lose an update. Typically, that's what happens. So that's a subtle bug in there. So let's try and do a little bit better. So I'm just going to change that, and I'm going to say, okay, instead of processing it in place, I'm going to process it and get a copy of the object and put it back in the map. But again, that's still a bug because you can have two threads actually running through this process. So each of those business processes will correctly, they won't corrupt the internal data because they're returning a copy, but one of those objects could win against the other. You might insert the copy of one and just drop the other one because it might overwrite the other one. So let's actually find a proper implementation. And this one just relies on some capability of the concurrent hash map. It's got a nice compute if present. It's got several compute if something or others. So this one says, okay, I'm going to access the object by identity, just as a map. And I'm going to say, if I have an update, I will process it, and the concurrent hash map is going to take care of any problem of concurrency there. It's going to do it sequentially. It's going to return, as you can see, it's going to return an object, put it in, but it's always going to do that sequentially. So I will never lose an update. I will always use it. So this is useful to know the capabilities of the data structures you're using when you're doing concurrent work. But as you can see, we've had to think about some subtle bugs to get to this point. So it's a little bit more effort. So this is the example of any implementation where it's just taking, in this case, remember I'm just using an update which is a double, but it can be anything. Here I'm just saying if I just incremented a state as an update, then that would be a bug in this situation. That second example, so let me just go right back there, the one that was also a bug, that was returning a copy. That would be like this second one, but again it doesn't work. And the third one finally here, process value idempotent. That's the one, the middle one here, and that is the one that works. But it doesn't scale brilliantly because the way the concurrent hash map has to do that compute, this one I'll just go back, the way it does this compute if present is it actually locks internally. It says, if I happen to have two processes, two threads doing this at the same time, the only thing I can really do is lock one of them and have it wait. So it's not fantastic. And then here's a final solution which would work all the way going back to our first bug. If I just replace that process value in place with this process value in place concurrent, that would work beautifully because I'm just using an atomic update. So that would be the fastest in this situation. But you can see how many options I've had to think about, how many different ways I've had to look at it to find the fastest one. And what's worse is that that's great if I've got one state, but if I've got multiple state, this doesn't work because I can't do add atomic to state 1, add atomic to state 2. That's already a concurrency bug. I'm updating state 1. Something else might be updating state 2 at the same time. So if I want to do something which is using multiple state within a business object, which is more typical, then I have to move halfway between an optimistic transaction and software transactional memory. Now, software transactional memory is a beautiful thing. It says, I take all of your changes, and then I'm going to do a commit, and as long as nothing else has changed any of the things I've changed, that'll succeed. If something else has already succeeded in changing some of the things I want to change, it'll fail. So that's very generic across all of your changes. You can quite easily do the equivalent within a business object for just your object. And this is how you do it. The way you do it is you take, you get the object. So if I'm going down there and I wrap the object, I use a wrapper around my business object. And then what I do is I say, okay, give me a wrapper, give me the current wrapper. Let me process the update, returning a new copy. And then I'm going to put that into a wrapper. And then I'm going to do this thing, which is compare and set, which is an atomic update of all my fields in one go. Because it's a new business object. And what I'm saying is that if I have the old object still there, then the new object will succeed. If the old object has changed, this will fail, done will be false, and I'll go back through that loop. This is fairly common. This is how you do multiple field updates in one go. It works nicely, and as long as the concurrency level is what most applications have, which is it tends to be more reads than writes, or even a similar number of reads and writes, then this is more efficient than locking. This becomes less efficient than locking only when you have a huge amount of writes compared to the reads. And if you get the slides, you can work through that. This is just so I was looking at that process value returning new, and this is showing you I've got two different states within the object. I can update them both, and notice there's nothing. This looks completely serial. So I'll just go back to that software transactional memory style. That is all in the framework that you would build. That's not in the business object itself. That's a framework. The business object itself, it's nice and simple. It looks serial. And that's the advantage of this kind of thing, is that where you put the effort is in the framework, or you can put the effort in the framework and make the business objects itself quite serial. But you do have to do this. You have to understand that you need to return immutable objects. So that was quite complex, to be honest. I mean, there was a lot of different subtleties there. There's a lot you have to understand about replay and atomic transactions. So it's kind of difficult. If it was me, I'd prefer to have a high-level model that do it for you. But you can do that. You can spend the time getting it right within the framework, and then your business objects you can build serially, that is the benefit. But you do have to spend time for your particular challenge getting it right in the frameworks. So you can see the disadvantages. It is kind of difficult. That's really the main disadvantage. Very easy to introduce bugs that you didn't think about. There was a lot of subtleties there. And this is why you've had, concurrent hash map is a nice and mature thing. Use that if you can. But this is why it took quite a long time for a lot of these classes in the atomic and the Java concurrent atomic classes to gradually come along. They didn't all come in Java 5. They've gradually been adding more and more because they're actually quite difficult to do. So that's two of the patterns. This third pattern is fronted by St. Paul's. If you've not seen it, it's a lovely place to go and see. Go across the Millennium Bridge, see the museums opposite. So this is queuing to a single thread. And this is going back to the single-threaded business object again. I always start there so you understand the differences. So queuing to a single consumer thread, I'm going to extend I'm going to call this the single-threaded class. That's the single thread. I'm just going to extend it and add a run method. So it's just a runnable class. I'm going to add a method. And all that does is it takes from a queue, and then depending on the operation type, it does either store or process update, or in this, I've added a flush. So the point is that I haven't really changed the business class at all. It's still single-threaded. It's nice and simple code. I've added this, which is kind of a template, so it's quite easy to do, to add this. It's fairly straightforward. And presto, I've got a single-threaded service that you can send stuff to. And on the other end, you create an API which takes your requests. So we have the single-threaded business object with its queue, and all it's doing is sitting there and running, taking objects off its queue, and it's running on a single thread, so you've got no concurrency issues. And on the other side, all you need to do is add to the queue. So store is just adding it to the queue. Process update is just creating a new business object, adding that to the queue and telling it to process. So if you come back to the queue processing, then you can see it's just taking the passed object, taking the identity and the value and passing it through as a single-threaded. This is actually quite simple. It might look a little bit sophisticated, a little difficult. It's actually really simple because it's single-threaded. On the receiver side, on the business side, it's completely single-threaded. You don't have to think about it at all. And on the other side, you're just adding it to a queue. That's all you do on the other side, on the producer side. So it's actually quite simple and straightforward. This is a rewarding shared state. That's why this works nicely. And it's got some nice advantages because you're decoupling the producers, the consumers. You get very nice fault tolerance. It's very easy to make it convert it into a distributed implementation. If you don't have to wait for the queue to be received at the other end, the object to be received at the other end, if you just add it to the queue and terminate, it's actually the fastest update you can do. Because you just add it to the queue and you say, okay, I'm going to trust that it's done and get on with stuff. So it can be spectacularly fast, as long as, of course, the consumer queue can take stuff off quickly enough. So it's a very nice potential solution for a lot of problems to keep it very simple. You just keep a lot of your code is just single-threaded, and you're just pushing off the effort onto that queue and adding one runnable. It's quite nice. It does have disadvantages because if you want to do bidirectional, so if you want to put the store and then get something back, or if you want to wait to guarantee that it's been updated, then it's going to actually have a higher latency because you have to wait for it to get processed at the other end. And if you want to get a response as well, then that becomes quite difficult because the queue is one way. You have to have another queue going the other way and an extra thread. So that becomes quite difficult. So it depends what you want to do. But if you just want to add it in and have the update processed, great. And you can use persistent queues. So that's quite a nice solution for a particular problem. And then this is a picture of Kota Bay in Montenegro. And that lady with a cat on her lap It's not her cat. Apparently that's famous for having lots of very nice cats around there that will sit happily on your lap and not claw you. So if you like cats, nice place to go. So this is the fourth pattern. It's partitioning the data. And the idea here, so we've gone back to the single-threaded solution again. That's where I always start, so you can see the difference. And let's have a look at the difference. The idea here is to split up into multiple data slots so that threads can update different slots at different times. So let's flick across there. I've replaced the map with a concurrent hash map because it's going to be concurrent. And I've just changed the method there, process value in place to process value in place partitioned. So this is the big disadvantage of this method, is that you can't put the effort into the framework. You actually have to put it into the business class. So this would be an example, a very simple example of processing it place partitioned. I'm just going to say, in this example, I'm just going to make 3 partitions. So it's got 3 states, and I'm just going to say whatever thread I'm updating in, I'm going to actually just get the ID, find the remainder when divided by 3, and I'm going to use that. It's 0, 1, 2. That's going to update one of these. So it's a pretty stupid implementation. So they could actually all end up having 0 as the remainder and everything update that. But it's an example. If you want to see a really sophisticated example, there's a Stripe 64 implementation in the Java, in the core Java, and it's amazing because it can actually, over time, improve its capability. While it's running, the more it's used, it tries to understand the threads that are accessing it, and it improves how it can spread the threads updating across the partitions it uses. Lovely thing, very complex to use. But this is the idea is exactly the same. I just say I'm going to have different slots for my data to write to, and I'm going to have each thread write to a different slot. And boom, I've got a very, very fast. So this is the fastest you can get. So there is a subclass of Stripe 64 which is called a long adder, and that's the fastest way of concurrently updating longs from multiple threads in the JVM. It's spectacularly fast. It does very nicely. So that's the advantage, is that it is the fastest way of doing updates, and the disadvantage is that it's very, very difficult to get right. And as you can see, as I've mentioned, it's also used for distributed systems. Cassandra partitions all the data and uses partitioning to decide where things are going to be written to, allows a very good throughput. Okay. I'm just going to see how I'm doing for time. Yeah, we're good. We're very good. So, you haven't slowed me down for any questions. I get you. You all get it. You will understand everything. Perfect. So this is Santa Lucia, St. Lucia, in the Caribbean. Who's been to the Caribbean? Nobody. Oh, man, I've always wanted to go there. I also haven't been to the Caribbean. Okay, or is it the Caribbean? Okay. So I'm going to put it all together. So how do you think about these 4 patterns? You can see that the pessimistic version, the locking version, it's quite easy. It's easy to understand, and it's easy to reason about. It's also easy to slip subtle bugs in there, letting data structures escape the classes. So that's the bigger thing, is try and have your data structures not escape the classes. And the thing about it is that because the JVM really understands locks quite well, it's usually fast enough for almost everything you're doing. It's only when you get to high levels of concurrency that it's not fast enough. So it's a good place to start. The optimistic transactions tends to be where a lot of people go to once that's not fast enough. Actually, a lot of people start at the optimistic transactions, and it's not unreasonable if you've got a single field and you're using the atomic classes. They're quite easy to understand, quite easy to use, but you have to understand concurrency because it's very easy to add very subtle bugs. Partition data is the fastest way to be concurrent, really hard. And then sending to a queue is the easiest if you want to add that asynchronous support or distribute. It's very, very nice and easy. So I did say early on, but just to remind you, these aren't mutually exclusive. You can use them all. In fact, that's also true of the high-level models. You know, the actors, functional programming, everything. There's nothing that stops you actually building an application with lots of the different components all together. So you can do actors and functional programming and thread DOI and atomic transactions all in a simple application if you want to. And the same with these patterns, these building blocks. You can use them together. And if you look at actual things that are out there, the concurrent hash map tries to be optimistic, tries to be lock-free, but it's not able to do that everywhere. So there are points where it has to lock. And it also, in order to improve throughput, it partitions the data. So the concurrent hash map is actually, it partitions the map into different slots. Different threads are updating different slots. And in fact, that's one of the parameters I think you can set how many threads you think it's likely to use. If you're going to go more than 32 threads, then you need to change that. So that's a good example. And then the actor model uses both of those. It sends to a queue and it partitions the data. And the reason it does that is to make sure that you can each actor is updating at the end of a queue as a single-threaded thing, but you have a lot of actors, so you don't want them all in one queue, you don't want them all in one thread, so it has to partition those actors across different slots so that different threads can pass the messages to the actors. And then the fork join pool actually uses every single one of these four systems. If you want to look through the fork join pool, it's all in there. So remember, this is all open source. It's quite complex, and but it's interesting. But it uses all of the patterns at various paces. So they're not exclusive. You can use them, and you use them how you mostly want. So I'm going to give you the step-by-step procedure you need to think about for your concurrent applications. And the first step is determine within your applications where the shared mutable data is. And that should be something at the design level, the architecture level. You need to do that as early as possible. It's not a premature optimization because it affects your whole design, it affects the architecture of what you're going to be doing. So you need to identify that as early as possible. And you don't just want to identify those state items, you also want to have a guess about the level of concurrency that's going to be used. So how many concurrent readers, how many concurrent writers there are for that data, that shared mutable data that you're going to have. And you need to do that as early as possible, but typically it goes a bit. You still, as early as possible means whenever you can, not necessarily at the design stage if you already passed that, but just go back and analyze your current design to see where you've got that. So step 2, having identified that, is eliminating one of those words, because that's the perfect solution. That gets rid of the difficult problems in concurrency. Any one of those words that you can eliminate. And obviously, it means that you have to restructure your design or re-architect your system to do that. But it's worth it, because concurrency problems are really subtle, annoying, and sharp at the worst and most annoying times. And if you can't actually eliminate it, then, as I said earlier on, maybe there's a data store, an external data store that's perfect for your use, and it's quite possibly fast enough. So think about that. So that's the second step. The third step is maybe you can use one of those high-level concurrency models. As again, this is, if you went to Russell's talk, he was trying to emphasize that we spend too much effort at these lower levels. And if we can go up to these higher levels where the models are, then that's really, really useful. That is enormously beneficial because they take care of the problems for you. And of course, you have to constrain how you program. You have to do it according to their capabilities. But there's gives and takes. And the most common ones that I've seen are those, but they're all in use. And you've got the whole list now, so think about what suits you and what works for you. So 1, look for shared mutable. 2, see if you can eliminate one of those. 3, if you can't, then try and use a concurrency model. 4 is, I can't even do that. I'm going to have to do it myself. And then, as you can see from the bugs we've talked about, that means that you need to understand concurrency. And there's the Brian Getz book. There's a few concurrency courses. Heinz Kibbutz is based on the Brian Getz's book. It's not simple. It's not straightforward. You need to spend time understanding these things. So, as I say there, the fork join framework, although released in 2011, was actually available since about 2008. So it's actually been in use in beta and so on for a decade now, and it still has bugs in it. And it's built by some of the best concurrency experts, and looked at by yet more of the best concurrency experts, and it's still got bugs in it. So it's a hard problem. So you're going to do it yourself. These are things that are important to remember. Do use what's appropriate. So think about the problem you're trying to solve. And now you've got a toolkit. You've got a whole toolkit. You know all the levels, you know the building blocks, you know the patterns, you know the models. You've got a toolkit, and you can mix and match those. Java will let you do any combination. So think about how it works for you. And then the thing about object-oriented programming is that good object-oriented programming always helps because it's all about encapsulation. And the more that you encapsulate your classes, your concurrency, the more it is shielding itself from the concurrency bugs that can happen. Like I said, you don't want to have the things escape the class. It's really important, especially for concurrency management. And then finalize everything, try and keep things immutable. That works really well to minimize bugs. And do explain why you're doing that in the code, because people are going to maintain your code, and they won't necessarily understand that. So this is a place where comments are very useful to explain. I have made these copies because it reduces concurrency bugs. So don't start thinking that you're going to make it more efficient by not making them copies. It's kind of an important thing. And the JIT does really well. Again, this is one of the things that the compilers, writers have optimized over the years, handling immutable instances. It does it very well. There are these closure-style classes. They're called persistent collections. They're not persistent in the sense that they live past the JVM or they live on the disk. They're persistent in the sense that if one thread writes to it, another thread doesn't see that write. It sees the old version that the structure was. So it's persistent across other thread changes. It's a different kind of persistency. And all of those closure style classes are actually available within Java because they were written in Java. So closure was built before closure. So all of those classes are written in Java. They're all available there, and they're quite good classes to to use to avoid concurrency bugs. They kind of copy on write. So if you've ever used the copy on write array, it's kind of that idea, but they're built differently. They're built more efficiently. And if you are going to do it yourself, there are a number of mature concurrent data structures, especially in those collections that I mentioned early on in one of the early slides. All those different collection groups implemented by different people. A lot of them are very mature. So my recommendation is that if it doesn't quite, if it fits perfectly, if it's solving your problem, that's perfect. But even if it isn't, can you adapt your problem so it uses one of those mature classes or a couple of them instead of you having to implement something? Because they're nice and mature, you can take the inefficiency, the overhead, the little bit of ugliness, and use something that's already mature in handling concurrency rather than do it yourself. And that's my advice, is that's preferable. But do look at the capabilities they have. So like that computive absence and computive presence for concurrent hash map. I rarely see that in use, but it's actually quite nice. So it's because people just assume I've got a hash map and it's a concurrent hash map, so I'll just do a very similar thing. And it has a lot of capabilities beyond that. Okay, so that is actually the gist of the talk. That's the full talk. This is me with, I might have skipped a couple of the pictures. This one is traveling in Naples, Italy, which is where I came back from last week. It's beautiful. And the Amalfi Coast is lovely, very, very picturesque. I recommend going there. That's not my picture. That's another winner of the Hotels.com competitions. My pictures are nowhere near good enough to win these kinds of things. And that's who I am. And questions, if I haven't saturated you. Yes?
I have one with this writing queue that you have. You have checked out the threads that reads from the state object. How does that solve anything for you?
If you have two threads writing to...
They read the same object and then they write to the store or whatever you do.
Are you talking about the queue to a single thread? So most applications do not have a huge amount of writes writing to an object. So as long as the consumer thread can process those writes fast enough, then it means that your business object is written completely serial. You don't have to think...
You read the same value from the same object, and then you do something to it, and then you write it back to the queue twice from different threads. So how have you now solved your parallel problem?
Okay, so you're processing one update?
I'm reading from the object, getting one. I'm reading once more, getting one. Then the first thread writes back, and the second thread writes back. I still have the same problem that I've done something to the same value twice, and they will overwrite each other.
I'm honestly not getting...
Well, it's different. It's a difficult thing to explain.
You're not updating the state from the thread, doing it from the queue. So you're not saying you can set this value to 4, you're saying increment it by 4.
Okay, so you're actually pushing a method onto the queue. Yeah, that was my idea.
Oh, okay. Okay, so if I go right back to that one, where are we? Queue on a single thread. What I have is a single thread, which is the consumer, and it's the producers are adding to the queue, but they're adding an update, so it's going to process the update. So if you look at the method there, process update, I'm passing in an identity and an update value. Here it's a double, but it can be anything. What I've done is I've reused the business object, but this could be a wrapper object, it could be anything. And all I'm doing is I'm passing that update. So the consumer thread will process that asynchronously. And because it's on a single thread, it's doing all the updates on that single thread. But it's taking a pipeline of updates. So that was, if you go back to the disadvantages here, if you do need bidirectional, so if I need to process the update and get a result, this is a difficult pattern to use in that situation. There's strengths and weaknesses, and that's one of the weaknesses of this one. You can still do it, and in fact, you can do sophisticated things like making the state over here in the queue. You can make it the state within the business object volatile, which means that you can see it externally, but you've got no guarantee. You will see a consistent state, but you've got no guarantee that that you're seeing a state including your update, because you don't know when the update was processed. So if you're going to require a synchronous update, so bidirectional, then you have to push your method onto the queue and then have another queue where the consumer thread returns it to that queue, and then your producer has to sit on the queue. So that's a pattern where you don't want to use this unless there's a very good reason, like, for example, you want to have a distributed application, and then it becomes feasible to do that because it becomes quite efficient and easy to do. So again, all of these are available online. If you can't see it, there's a reference at the bottom there. It's fasterj.com/jaxlondon2018.zip. Excuse me. And the slides are all there. And it's fairly self-contained, so you should be able to go through the slides. There was some explanations, but if you've been here to the talk, you should be able to go back through the slides yourself and understand most of it. The only thing that's really quite difficult is the optimistic transactions where you're updating multiple fields at the same time. And you'll probably need to look up an example for that, because that really needs the full code for you to understand. But the basics were there. It's the core item there is in that slide. Any other questions? No? Okay then. Enjoy yourselves.